Welcome everyone, my name is Piero Rivera Benois. I work at the Signal Processing Group at the University of Oldenburg, and today I'm going to present you our latest results on the sound pressure minimization at the eardrum for in-ear ANC headphones using a virtual sensing technique. The outline of today is going to be the following. First, I'm going to give you an introduction into the topic of ANC headphones, followed by a general description of how virtual sensing algorithms work. Third, I'm going to describe the proposed procedure that we use to optimize a fixed feed-forward ANC controller when we only have an external microphone at disposition by applying a virtual sensing algorithm called remote microphone technique. Fourth, I'm going to present the simulation results that we achieved by means of acoustic transfer functions measured with a real device and a dummy head. Finally, I'm going to finish this presentation with a summary of the most important findings of our work. ANC headphones aim at minimizing the environmental noise at the listener's ear. These devices combine the passive attenuation achieved by the construction material of the headphone and the active attenuation achieved by means of ANC. While passive attenuation is mainly effective in the mid and high frequencies, ANC is mainly effective in low frequencies. At your right-hand side, you can see a typical in-ear headphone. It is equipped with an external microphone, an inner microphone, and a loudspeaker. The wave of the incident noise first arrives at the external microphone as X of n, then travels through the device until it reaches the inner microphone as R of n, and finally reaches the eardrum as D of n. Simultaneously, the ANC controller generates the signal minus U of n to drive the loudspeaker, aiming at generating a sound wave that destructively overlaps with the sound wave of the incident noise. Virtual sensing works using a two-stage approach. In the first stage, called the calibration stage, an audiological probe tube is placed at the eardrum, depicted here in pink. With the DSP depicted in blue, the loudspeaker to microphone acoustic paths are measured. Afterwards, subject to the noise sound field, the microphone to microphone acoustic paths are measured. If a fixed controller is considered, now it will be optimized considering the measured acoustic paths. During the second stage, called the control stage, it is assumed that the measured acoustic paths are time invariant. Hence, the audiological probe tube is removed, but the measured acoustic paths are incorporated in the ANC algorithm to make online approximations of the sound pressure at the eardrum. This is done by following a three-step approach. First, the estimated acoustic path P of R is used to cancel the control signal at the position of the inner microphone, and through this, estimate the noise sound field at the inner microphone as R of n. Using the estimated signal R hat of n, together with the microphone to ear acoustic path M of Z, the noise sound field at the position of the eardrum is estimated. Third, using the estimated signal D hat of n and the secondary path S, an approximation of the sound pressure at the eardrum, E of n, is done. The estimated signal E hat of n is then used to adapt the controller W, for instance, with the FX LMS adaptation algorithm. In this work, we consider an in-ear headphone equipped with only an external microphone and propose a robust design procedure based on the remote microphone technique to compute the controller W, aiming at minimizing the sound pressure at the eardrum. The PSD at the eardrum can be written as follows. The left-hand addend determines the minimum achievable PSD at the eardrum, which is 0 when the magnitude square coherence between D of n and X of n is equal to 1. The right-hand addend defines the scope of optimization of the controller W. Here, the controller and the feedback path Px build a transfer function that in series connection with the secondary path S should approximate the microphone to ear acoustic path phi dx divided by phi xx. Since the signal at the eardrum cannot be directly measured during operation, we use the acoustic transfer functions measured during the calibration stage to optimize the controller's impulse response for what we call a calibration sound field. With this calibration sound field, we approximate the PSD of X and the acoustic path Vdx divided by Vxx. Aiming at increasing the robustness of the controller against reinsertion of the headphone, we propose to simultaneously optimize over frequency for several measurement repetitions of these acoustic paths. Depending on the headphone design and the construction materials, the feedback produced by the feedback path Bx can be sometimes neglected. However, in the general case, it is required that the optimization is subject to a stability constraint, so that the resulting controller yields a stable system, as the one shown below. In the first experiment, we evaluated the influence of the calibration noise field on the system's attenuation in free field. For that, we considered only one headphone insertion. We estimated the PSD of the signal at the external microphone and the transfer function between the external microphone and the eardrum from three different calibration noise fields. Using this, we optimized 3 controllers. Using the same headphone insertion, we evaluated the system for white noise coming from different DOAs in free field. On the polar plot at the right-hand side, we see the results. The controller optimized for the ipsilateral side, shown in blue, shows a large DOA dependency. It achieves minus 20 dBs of attenuation when the DOA matches the one of the calibration sound field. Moreover, it achieves minus 10 dBs for DOAs that extend to plus 45 degrees and minus 65 degrees from the ipsilateral DOA. With the controller optimized for the contralateral side, shown in red, similar attenuation results could not be achieved for the contralateral DOA, probably because for the DOAs in the contralateral half hemisphere, the performance is limited by a low causality margin. The controller optimized for a diffuse field, shown in yellow, shows an attenuation of at least minus 10 dBs for the whole ipsilateral half hemisphere. This is probably explained by the shadowing effect of the human head, which weights the DOAs of the ipsilateral side more. In the second experiment, we evaluated the influence of a headphone reinsertion on the system's attenuation in free field. For this, we considered the previous controllers, and without re-optimizing them, we took acoustic paths from a different measurement repetition for the evaluation. It can be seen that after the simulated reinsertion, an attenuation of at most minus 4 dBs can be achieved. Moreover, even when using the controller optimized for the ipsilateral side and exciting the system from the ipsilateral DOA, still no more than minus 2.5 dBs of attenuation could be achieved. In a third experiment, we evaluated the influence of the simultaneous optimization for several measurement repetitions in the system's attenuation in free field. For this, 2 controllers were optimized for 7 measurement repetitions of the acoustic paths. Afterwards, the evaluation with the unseen case was repeated. It is clearly visible that both new controllers significantly improve the attenuation in the ipsilateral half hemisphere. With the controller optimized for measurement repetitions under an ipsilateral calibration sound field, achieving slightly better results than the controller optimized for measurement repetitions under a diffuse calibration sound field. Hence, optimizing for several measurement repetitions produces rather good results. So, we have come to the summary of this presentation. Today, I've shown you a robust optimization procedure for sound pressure minimization at the eardrum, which follows a 5-steps approach. First, we place an audiological probe tube at the eardrum. Second, we measure loudspeaker to microphone acoustic paths. Third, we play back a calibration sound field and measure with it the microphone to microphone acoustic path Vdx divided by Vxx. We repeat the first 3 steps until the amount of measurement repetitions is reached. We have found that 7 repetitions is a good starting point for that. Afterwards, the controller W is optimized for all measured acoustic paths simultaneously. Finally, the audiological probe tube can be removed and the ANC headphone is reinserted in the ear and turned on. During our experiments, we have found that, first, the headphone reinsertions have a much larger effect on the attenuation than the calibration sound field. Second, To optimize simultaneously for several measurement repetitions is an effective countermeasure against the effects produced by reinsertions. Third, the ipsilateral and diffuse calibration sound fields produce similar results. So the scientist or engineer can choose between both, considering that, on the one hand, the ipsilateral calibration sound field requires only one loudspeaker for its generation, but potentially a longer measurement routine as only one ear can be calibrated at a time. And on the other hand, the diffuse calibration sound field may require more loudspeaker for its generation, but both ears can be calibrated simultaneously. So this is all from my side. I'm looking forward to reading your comments and answering your questions in the chat box. Bye.